Hello and welcome to TI Precision Labs. In this series, we're going to discuss Serial Digital Interface, or SDI. Today, we're going to discuss a video pattern used to test SDI retimers called the pathological pattern. First, we're going to review the origin and negative effects of the pathological pattern, namely in baseline wander, and continue by showing how a retimer can counteract the effects of the pattern. Lastly, we will discuss a practical test that uses the pattern that shows the effect of an increase in capacitance on the input to a retimer. In broadcast video applications with SDI, cameras output video data through a long single-ended 75-ohm coaxial cable to a line card. Retimers on the line card will then equalize and send a clean version of the video camera data to an FPGA for processing and overlay. For an example, think of a live football game. During the game, many cameras are simultaneously sending video data over long coaxial cables to the control room for further processing. Because of the length of the cables, a retimer is often needed to ensure that the video data is free from inter-symbol interference and jitter from equalizable and non-equalizable sources. Retimers are there to make sure that you don't miss that touchdown. The Society of Motion Picture and Television Engineers, or SMPTE, defined a standard for the SDI protocol that includes a scrambler to encode the data and maintain DC balance. However, there is a flaw in the equation used, namely that when a magenta and gray static image is applied to this scrambler, it results in a DC imbalance pattern with 1 1 and 19 zeros, repeated over and over again for several microseconds. A complementary pattern consisting of 19 ones and 1 zero is equally likely to occur. These DC imbalance patterns, called pathologicals, can be several microseconds in duration, and they pose a significant problem in these systems. Consider this system with a transmitter followed by a cable with an AC coupling cap connecting to the receiver chip as shown in the typical SDI system block diagram above. When the data pattern is DC balanced, or PRBS-like, there are no issues and the eye diagram at the equalizer output looks clean. However, as soon as the pathologicals arrive, the AC coupling capacitor blocks the low-frequency information, resulting in baseline wander, where the waveform shifts down and up, leading to increased jitter and reduced eye opening, thus affecting margins if left uncorrected. Now that we've defined baseline wander and the pathological pattern, let's take a look at how baseline wander is corrected. Like we saw earlier, when the pathologicals arrive, the AC coupling capacitor CC blocks the DC content. When we see 1 0 and 19 ones, the DC content of the transmitted waveform is very high. See figure TX in the diagram for an example of this. Since the capacitor blocks the DC content, the voltage on the other side of the capacitor shifts down accordingly. See the figure labeled CTLE out in the diagram for an example. Now, if we quantize this signal by passing it through a limiting amplifier, we can get a replica of the transmitted waveform, labeled LA out. However, this replica is not perfect because the baseline wander has caused a large amount of jitter. If this replica TX output is filtered with a low-pass filter with the same cutoff frequency as the input AC coupling capacitor CC, then we can recover the low-frequency content in the data. For an example, see the waveform marked BLWC out in the diagram. Adding this BLWC out signal to the CTLE output, we can thus cancel the baseline wander, resulting in a clean eye at the linear output and at the limiting output. This architecture is commonly referred to as a quantized feedback. Now that we've discussed a method to correct baseline wander, we're going to go into a way of increasing the amount of baseline wander. As we've discussed, the AC coupling capacitor previously labeled CC, is an instrumental part of the baseline wander prevalent to the pathological pattern. In the following few slides, we will be discussing the effects of changing the AC coupling capacitor value. The test is set up as follows. First, the pathological pattern is generated by the video pattern generator. Next, the pathological signal is routed through a 1 meter 1694A coaxial cable to an LMH1297 cable driver. The LMH1297 cable driver has an adjustable capacitance on its output. This means that the AC coupling capacitor on the input to the device under test is a series combination of the two capacitors and is adjustable to many values. The signal is then either retimed by the DUT and passed through another 1 meter Belden 1694A coax cable to a video analyzer to see bit errors, or it's routed at the output of the 1297 to a real-time oscilloscope to see the baseline wander on the input of the DUT. As you can see, baseline wander is proportional to the equation shown in the bottom right of the slide, where constant 1 is related to the average pathological voltage, constant 2 is the width of the pathological signal, and the time constant is proportional to the total capacitance on the input, including the AC coupling capacitance. One thing to note is that with lower input capacitance, the baseline wander increases, and at high baseline wander values, it is likely to see bit errors on the video analyzer. Now it's time for a quiz. Be ready and pause the video after each question so that you can take some time to answer. When using the pathological pattern, does a higher AC coupling capacitor on the input increase or decrease baseline wander in millivolts? The answer is decrease. Next question is, does baseline wander correction involve a feedback RLC circuit? True or false? The answer is false. For a bonus question, what year was the first SMPTE standard introduced? 2004, 1976, or 1989? The answer is 1989.